So question number 1. Determine the resultant internal loading acting on the cross section through point C in figure 1. Okay, internal loading at point C. Yeah? Assume the reaction at support A and B are vertical. So A, here's A and B. So the reaction are vertical. So we have AY and also BY over there. But now the question wants us to find internal loading at point C. So later you need to cut here at point C. Yeah. Okay. So the first step that we need to do is to draw free body diagram of the original figure. This is our original figure. Then I will draw free body diagram. Okay. To find the unknown. So at point A, we have AY. At point B, we have BY. And then, here in the middle, we have point D. Right hand side is 6 meters. Here is also 6 meters. Yeah? So it's mirror A and Y, and then the center point divide that two areas, 6 meters, 6 meters. So we can say that it's like a mirror. Left and right are the same. And then if you can see from this figure, the triangular shape of distributed loading, left and right are also similar. With the value is 6 kilonewton per meter, and the other one is also 6 kilonewton per meter. So, as I explained to you in previous class, when we have distributed loading, here and here, okay, we need to convert these two loading into a single load. For triangular shapes or any other shape, to convert it into single load, then we need to calculate the area. So this is the area, triangular shape, the area of this shape, and the area for the second shape. Yeah? So the first shape will be half the area, half times the base is 6, 3 plus 3, and the height is also 6. So half, okay, times 6 times 6. So total will be around 18 kilonewton. Yeah. But the placement of the single load should be, as I said to you in previous class, if we have triangular shapes, so you want to convert it into a single load, it will be like this. So this is the total length L. This is the total length L. Okay, to convert it into single load, then it will be here. Okay, yeah. This is L. So L equals to 1 over third times total length. Okay, so here we have 6 meters, and then 1 over third times 6, it will be 1 over third times 6. Okay, 1 over third times 6, then it will be 2 meters. Yeah. So the placement is like this here, 2 meter, and then the remaining will be 4 meter. And also the same thing here, we will have 18 kilonewton over here. This is 2 meter, this is 4 meter. Okay, so you have AY 18 kilonewton over here, 18 kilonewton at this point, and also BY. Then you need to solve these two unknowns. Okay, so I'll do it together. I will take point A as my reference point. So summation of moment at point A equal to 0. Okay, so I have 18 here. Distance to point A is 2 meter. Okay, the arrow is going down. it will rotate to point A clockwise. Clockwise, we'll put negative sign here. And then I have another one, 18 over here going down, rotate to point A, also minus 18. But now distance is 4 plus 4 plus 2 is 10. And the last one, BY going up, counterclockwise to point A, plus BY times 2, 4, 4, 2, it will be 12, equal to 0. Then BY equals to 18 kilonewton. So to find AY, very easy. Summation of FY equal to 0. We have AY going up, plus, then minus 18, minus 18, plus BY going up, plus BY equal to 0. BY is 18, yeah? Then finally, you will get AY also 18 kilonewton. So now we have the unknown, AY and also BY. Then the next step, after we have the unknown, we need to draw another free body diagram that relate to the internal loading. So the question is, what is the value when we cut at point C over here? So I will cut that section. And okay, so this is from A to C. Let's say this is AY. AY is 18, yeah? Then when I cut at point C, I have normal force, shear force, VC, and also bending moment at that point. Okay, there will be 3 parameters here. Then if you can see from A, okay, from A, this point, to C, we still have distributed loading over here. But it's not fully triangular shape, it's like a trapezium. So you will get around like this. Okay. Okay. So it's like a triangular shapes. It's not fully triangle, but like a trapezium. We know that the height over here is 6 kilonewton per meter. But how about this height? Okay. So from the original figure, okay, the length from this point, just focus on the triangular shape from this point, okay, till this point, okay, these 2 points, okay, I'll draw, okay, from this point to this point, okay, this is 6 meter, okay, 6 meter, 6 meter, okay, 6 meter, 6 meter, the height is 6 kilonewton per meter. If 6, the distance 6, then the height will be 6 kilonewton per meter. Okay, I want to make a ratio. Now, from A to point C, because we want to cut at point C, distance from A to C is 3 meter. So the remaining distance should be 3 meter lah. Okay, if I draw the full triangular shapes, then this is 3 meter, this is 3 meter. If 6 meter, the height will be 6. If only 3 meter, then the height here will be 3 kilonewton per meter. Can you get it? 6 meter, the height is 6 kilonewton per meter. If I cut somewhere here, if I have 3 meter, then the height here will be 3 kilonewton per meter. That's why here we have 3 kilonewton per meter. Okay. So from this figure, we can divide it into 2 shapes. The first shape is triangular shape, the upper one. Okay, this is triangular shape. The lower shape is rectangular shapes. Okay, so as I said to you in previous class, if we have distributed loading, then we cannot calculate. So we need to convert these two shape into single load. Okay. So I will solve the upper shape first, the triangle shape. So total height is 6 and the lower height is 3. Okay, this is 3. So same here is 3. So the remaining one will be 3. 3, yeah. 3 kilonewton per meter over here. 3 kilonewton per meter on the upper area. So to convert it into single load is the area of that shape. The first shape is 6 kilonewton. The height, the base is 3 meter. So triangular shape basically is half times 6 times 3. Half. So the first shape will be half times 6, the height, and also the base, 3. So 18 divided by 2. Sorry, this is not 6, 3. Total height is 6, but the upper height is only 3, sorry. So this will be 3. So 9 divided by 2 is 4.5. 4.5 is here. 4.5. Okay, 4.5. Distance here is 1/3 times total length. Similar. 1/3 times total length. Total length is 3. 1/3 from 3 is 1 meter. So here is 1 meter. The remaining will be 2 meter for this single load. Okay. And then we have another one. The rectangular shape on the lower part. So 3, the height, times the length is 3 meter. 3 times 3 is 9, yeah? So 3 times 3, 9. This is rectangular shape. So to put the single load, it will be in the middle of that shape. So here, somewhere here, 9 kilonewton. Okay? So here is 1.5, here is 1.5. For that loading only, 9 kilometer. So it will be in the middle. So if I draw it back, okay, if I draw it back, so it will be something like this, yeah. Okay, this is our beam. Okay, if I draw it back to make it clear, this is 18, AY, yeah. Then we cut here, we have that three things lah. Normal, force at the point C, shear force, and also here, bending moment, point C. So we'll have that three things similar. And then here, over here is 4.5, the triangular shape over there. And then in the middle, here, I have another force, 9 kilonewton. 9 kilonewton refer to the rectangular shape, the lower area. So here is 1 meter. We'll divide it. This is 1 meter. 3 meter. Total 3 meter. So this is 0.5 meter. This is 1.5 meter. So total will be 1.5 plus 0.5 plus 1. Total will be 3 meter, similar to this original figure. Okay. So from this diagram, we need to find NC, VC, and also MC, the internal loading. Okay, we do it. Now, okay, first, how to find NC, normal force, So summation of Fx equal to 0. For sure, from this figure, there is only one force, NC, on the x-axis value. Then straight away, you can say that NC equal to 0. Okay. Second one, VC. VC is in y directions. Fy equal to 0. We have 18 going up. Okay, 18 going up plus, yeah. Then we have 4.5 minus going down, minus 9 minus VC equal to 0. We arrange back that equation. VC will equals to 4.5 kilonewton. Okay. And the last one, moment, yeah. Summation of moment equal to 0. So I will start with the last force from here. This is our cutting point. So 18. Distance from 18 kilonewton to this cutting point is 3 meters. Okay, 3 meters. The arrow is going up. It's going up, and then it will rotate at this point, point C. So clockwise minus here. Then I have the second force, 4.5. Distance until point C is 1.5 plus 0.5, 2 meter. Okay. The arrow is going down. See? The arrow is going down, then it will rotate at point C, counterclockwise plus. Okay. And then I have the last force, 9 kilonewton over there. Also going down, rotate at point C. So plus 9. Distance from 9 kilonewton to point C is only 1.5, yeah? 1.5 equal to 0. No, not equal to 0. Yeah. Okay. We have another one, MC here. So don't forget this MC. This is what we want to find. So, not finished yet. The arrow is counterclockwise. Okay, the arrow is counterclockwise, meaning that plus MC equal to 0. So we have plus MC equal to 0 here. As usual, you rearrange back this equation. MC equals to 36 kilonewton meter. So this is how you solve question number 1. First, you draw the original figure, then you find the unknown, these two unknown, AY and BY, then you move to the next free body diagram by just draw the diagram that relate to that cutting point. So this is our cutting point, point C. Convert all the distributed loading into a single load like this. Then after that, you have all the forces here, all the dimension here. Then you can find that 3 parameters in internal loading. For Fx, mostly for NC, if you write down the equation of Y equal to 0, then you will get the shear force. And the last one, moment at point C. So then finally you will get the final value. That is 36 kilonewton meter. So this is how you solve question number 1, right? We'll move to question number 2. Okay.